Wonderful. Great. Great to meet you all. Apologies in advance if my voice is a bit broken. I'm still recovering from COVID, but I think I'm all, patched up enough. I want to start with, my journey of feature platform. It started several years ago. I was at Quora back then. I started the machine learning infrastructure efforts, and I gave a talk in 2017 talking about open source ML systems that need to be built out. And I talked about two layers of the very nascent MLOps stack. One was model management, the other was feature extraction framework. And I went on to describe what I thought, based on the needs we had already experienced at Core, what a good feature extraction framework may look like. Those were the early wild west days. You can see I was calling it feature extraction framework. The term feature store did not exist yet back then. And so, I gave this talk, I presented what I thought were, obvious ideas, and I moved on with my life. I from there went on to, work at Facebook. I at Quora, I read several quality abuse risk related teams. At Facebook, I was closer on the Rexis side, and some on, for, integrity, but not fraud space really. Eventually, I ended up, running a large part of the team behind PyTorch as well. And each of these experiences was, quite transformational in many ways. Through Quora, I first started understanding the problem from first principles. At Facebook, I saw, what three generations of a, solution for this looks like. Kid you not, Facebook has, I think as of right now, over 100% organization working on the feature engineering system. I saw real time, gaining adoption and becoming very important everywhere. And at PyTorch, I truly, got doctrine the school of, beautiful Python APIs is all that matters. And if you can make people productive, everything else can follow from there. When I was leaving Facebook, I was, thinking of doing my own startup. I looked around, and to my surprise, the deck that I had put out in the open in 2017, I still didn't find a feature store, as it was called, by then. I didn't still find a feature store that more or less, lived up to the manifesto I'd created. And so we just decided to move on and do that. And that's what I'll be talking about in today's discussion. What Fennel does, and how it is so different from a lot of other options out there, and what is the thinking process behind that. For the first few minutes, I'll spend maybe 5, 7 minutes, not more than that, just literally walking you through some code snippets of what does it feel like to write, features in Fennel. This is important because it sets the tone for the rest of the conversation. After that, we'll talk about a handful of choices that are very, countercurrent right now, very unique choices in, the constraints we are taking. And finally, depending on how much time we have, we can go a little bit deeper into the infrastructural choice, like specific, nuts and bolts of how things work together. But first, I'm gonna keep sharing my screen, but open Fennel docs and walk you through a few code snippets to help you understand, what's the experience actually feeling like. Fennel has two main abstractions: a data set and a feature set. I'll only talk about data set right now. We don't have enough time for a full walkthrough. Data set is effectively a table of data. This is a data set called product. It has 5 columns: product ID, seller ID, price, and so on. Each of them has a type. As you can see, the schema is written in a Pydantic inspired manner. You have some metadata, owners, and tags, and so on. And more importantly, here we have system telling us that we should be looking at Postgres table called product info every 1 minute and using whatever new updates have happened there to hydrate this dataset product. In other words, this dataset product is going to be a near real-time mirror of your Postgres table product info. And if your data did not live in Postgres, we have, let's say it lived in Kafka, we have different decorators for all of those systems. All that changes is the source decorator, but wherever the data lives, whether it is, S3 or, Snowflake or Redshift or Kafka, Kinesis, Postgres, MySQL, wherever data lives, we know how to get it. All you need to do is define the schema in a Pydantic inspired manner and put the source decorator on top of that. But quality is a very important concern for us. It's a top 3 design decision for us. And so there are a bunch of small primitives already for you to start elevating your data hygiene. So for instance, you have a very strong typing system. Here, for instance, if we see a description, it can be string or it can be null, that's fine. But if we see a price that is null, we would not even admit that data in the data set. More generally, we have strong typing, and so anything that does not meet your types does not get admitted into the data set. We have new types as well. We have a type for regex match where you can say that only those strings satisfy this type that, let's say, the zip code regex, and only valid zip codes at the type system level are enforced to be present in the column. So downstream users don't have to do defensive programming. There's just one primitive. We have many more primitives. Here's another one I want to show you right now. We have native data expectations. So in line, you're able to describe that you expect the column price to be between 1 and 10,000 in at least 95% of the cases. This is a lot like great expectations. In fact, it is literally built on top of that. But this is computing these expectations in a streaming real time as new data is arriving, and you can set up alerts against that as well. Now, all I've shown you is wherever data lives, you can bring it to Fennel and start elevating the data hygiene. But more often than not, you want to derive more data using the data set that you already have. So imagine this is a data set you wish to derive, which given user ID and seller ID is counting the number of orders from that user on that seller in last 1 day and last 1 week. So a typical rolling window aggregation, a very common in feature engineering. This is how you would write that pipeline. This is a function in the class. You're saying I'm starting from order and product datasets. These are the datasets I showed you earlier. You're saying if I know these two, I know how to derive this out of it. And now order gets bound as a function argument here and product gets bound as a function argument here. And you can now describe all your pipelining logic. You can join, you can transform, filter, add rows, add columns, all of that. Now, there are many things that are really nice about this. I'll highlight a couple and I'll go back to slides after that. The first thing that's really nice is it's extremely declarative. You're not having to think about, where should this run, how much RAM should be given, what if data doesn't fit in RAM, how should be partitioned, how should be scheduled, is it waiting for an upstream job to finish? You don't have to think about any of that. The second thing that's really nice about this is very, very Python native. This is an actual Python Lambda, a free-form Python Lambda that will be executed against every row in this data set. This is an actual Pandas data frame. And so all of Pandas API is transparently available to you. You can import your favorite Python libraries and start using them as a part of this Lambda. So if you know Python, if you know Pandas, you know how to use this, and you can bring the full firepower as well. The most important thing is this is actually a streaming pipeline. It looks really simple to write, but as new rows or new updates arrive in orders and or products, this logic is executed incrementally only for the new data. And this data set is updated wherever those updates happen. And that process is happening continuously. And the exact same code ends up powering irrespective of order itself coming from, let's say, batch sources like S3 or Snowflake or Kafka, or same for this. None of that matters. The exact same code powers, and you're now able to bring data from multiple places in the same plane of abstraction and act on that. That's all I want to show you right now. Now, with this flavor in mind, now let's talk about some of the interesting choices we have made that are somewhat counter current right now. To simplify the authoring experience, as you can see, we let people write pure Python with Pandas. There's no DSL involved. There is no PySpark involved as well. And so benefit of this is, people, ease of use is obviously there, but they can interop with full Python ecosystem as well. And this is straight up, a page, we took from the PyTorch playbook. And our belief is we need to meet people where they are. I think what I see a lot of other technologies in the industry doing, this is what TensorFlow did as well, until PyTorch came and started beating them, is build the experience with performance in mind. Whereas I think what PyTorch did was they said experience is important and will solve performance at lower levels by doing a lot of innovation, which is what we ended up doing this. How do we then solve performance? We built everything in Rust. We do very fast Python Rust interop. We literally embed the Python interpreter inside our Rust primaries. And some of the new improvements that are coming in Python, where GIL is not a problem anymore, it actually turns out to be a lot more feasible than we initially thought early on. On the data computation side, Simba earlier mentioned that most use cases are batch. That is true, but we also found that almost everyone has some streaming features, and people are not comfortable having two different frameworks, some for streaming, some for batch. And we also believe that the utility of streaming is only going to go from here. And so what we did was we have no separate batch or streaming subsystems. There is no place in the product where you annotate and say this is batch or this is streaming. The exact same code works for everything. Everything is streaming all the time. It's built on Kappa architecture. And not only it makes the system future proof, it ends up removing a ton of complexity from the end user. Like for instance, backfilling a streaming pipeline is so terrible because backfilling is inherently a batch oriented operation, but the streaming pipeline going forward, it needs to do streaming. It's resonance mismatch. And so, this completely eliminates all of those interaction modes. And the way we were able to do this is we literally wrote our own stream processing system written in Rust, very memory efficient and purpose built for this kind of operation that becomes common. There's another element of real time, which is what are sometimes called as on-demand features in our world. As we spoke with more and more companies, we discovered that people want features to be able to depend on each other recursively and derive from that in arbitrary ways. And there are also many features which you have to do some more interesting processing. So we came up with this abstraction called read-write separation, where our features are not stored data, but rather they are stateless functions. And those stateless functions run on the read side of the request is waiting, whereas all the computation that is asynchronous via pipelines is happening on the write path. The write path is throughput oriented, but not latency bound. Read path is very latency bound, but usually not throughput oriented. And you now have the ability to keep some computation on write path, some on read path, all on write path. You can pick and choose how you want. And what this ends up doing is very flexible feature patterns become possible. So for instance, if let's say in recommendation world, which is my world at Facebook, a very common feature is dot product of user embedding and content embedding. That's very hard to express because you have to do that computation on read side. You cannot pre-compute order n square user item dot products. But by keeping it on the read, but keeping some other computation on the write, it becomes quite natural to express as well. To simplify quality, this is another thing that we kept hearing. We just went ahead and made a native best-in-class tooling and added it to the product itself. And literally what we did is, we asked ourselves, what are all the quality problems we've ever seen in our lifetime related to features? And for each of them, we asked ourselves, how do we design a solution against them? Can we catch them at compile time? Can we catch them upstream? If not, if none of those preventive mechanics work, can we diagnose that somehow? Can we do monitoring, etc. on it? And so what this ends up doing is, as people's features get more complex, the confidence still stays up. And everything from versioning, immutability, strong typing, data expectations, drift monitoring, unit testing, all of that just natively part of the product itself. Here I'm showing a couple of screenshots of drift monitoring and data expectations. Very contrary to the very previous speaker, we actually to simplify operations, we do deep vertical integration. We are highly anti-virtual. We find that when we are starting to research into this, is existing feature stores need people to bring their own KV stores, their own compute engines, own Spark, own metadata stores, sometimes own Kafka as well. And you could make a case that customer already has some of them, but in practice it is a lot harder than that. There's a lot of operation work and more importantly cost work as well. Redis and Dynamo actually do not work for a lot of people at scale in terms of cost. And then even if cost is not an issue, operation is not an issue, shared dependency then leads to a lot of confusion. Like who does auto scaling of a shared Spark cluster as an example? What happens if some jobs are failing? Who's on the on call for that? And so this is a very counter culture choice, but what we have done is whatever Fennel needs, we bring that up and manage all of that ourselves. And there is zero dependency installation for the end customer. Obviously, this increases our surface area quite a bit. We have to do as good of a job running everything smoothly in a cost-effective manner, in a compliant manner. But as always, every step of the way, the choices we take are make it easier for the end customer, make it harder for ourselves. Taking a page from the PyTorch playbook, so to speak. And finally, to simplify InfoSec, this is also a counterculture choice we made. We we do also have data planes and control planes, but our data planes are rather thick and control planes are absolutely tiny. And as a result of this, what happens is our control plane can literally go down and your workflows will not be interrupted at all. In other words, our data planes are thick enough to be nearly self-sufficient. Even the auto scaling lives inside data plane. Even the console UI where you see the code of your features lives inside data plane. So your data and the code of your features are never really leaving your data plane. Now, all of these choices, literally every single one of them, requires us to solve hard engineering problems, but it ends up creating, in our admittedly biased view, a much superior experience for the end data scientist. Now, I probably don't have time to go through all of these, but I'll just walk through a couple of these things real quick. As I mentioned, we built up our own streaming engine. We had to satisfy the constraints that we created for ourselves. I'll just walk you through a couple of choices related to those. One very important choice we made, by the way, this section is now going a level or two deeper than the rest of the conversation. We have built up our streaming system in a way that there is no synchronous communication everywhere. It's a full shared nothing architecture. Unlike Flink, where operators communicate with each other via RPC calls, which has some benefits, but it has some downsides as well. Fennel does not do any of that. Communication is either within a node, so in memory channels and so on, or it is asynchronous, mediated via Kafka. And since we use Kafka, it naturally handles back pressure, backfilling, things like that. A single node can go down, many nodes can go down, and everything else continues making progress without any interruption. And we also get exactly once processing for free as a result of this. We use RocksDB for managing the state store of our streaming jobs. But there are several interesting choices we made here as well. All the writes during iteration are buffered in memory, and they are applied together atomically later. This maintains the exactly once processing, and our jobs as a result of this can die anywhere and can wake up on any other node of the cluster, and they'll continue working. We are taking periodic backups using EFS. I don't know if any of you are using EFS for backups, but really, really good tool for that particular problem. And we also store some transaction markers in Kafka so that if we have to do recovery, we do optimistic recovery, we are able to do that effectively. We are doing continuous checkpointing. This is one of the bigger problems with Flink. Flink checkpointing model is stop the world, which means every time you're writing a new feature, the topology is changing, which then means that you need to stop the world for a few minutes, which creates a lot of lag, not acceptable. In our model, every job is checkpointing itself continuously, independent of other jobs. So it's distributed checkpointing. The local SSD checkpoint happens every second or so. So the processes could die and wake up again on the same machine, and they just literally pick up right where they started. And we do persistent checkpoints across machine boundaries using object stores every few minutes. And so if the whole machine dies and we have to bring up the job on a different machine, it first spends a few seconds catching up and then continues processing from there. The benefit of this is the system becomes much simpler for us to operate. It's quite literally built for resilience in mind. A node can go down and there is no issue whatsoever, and we can still get fast recoveries. Now contrast this to what a customer may have to do if they were to run Flink on their own and handle these kinds of issues. One very common problem with Spark and to some degree Flink in feature engineering world is they run out of memory. I mean, they generally happen for all data engineering jobs, but particularly for large rolling window aggregation jobs in feature engineering. We have built up a stream processing engine in a way that there is no in-memory state of jobs. State always lives on disks. And in practice, it's built up in a way that it lives in either the OS page cache or block cache of RocksDB, maybe mem tables. So we still end up not creating that much overhead in reading and writing from it, but the state does not blow up no matter what. And OS transparently pages out certain memory if it is not needed so that it does not go out of memory. In addition to that, we don't do any in-memory shuffle operations either. As I mentioned, all communication is mediated via Kafka. We don't use JVM. We write things in Rust. There is no GC, so memory cannot go up temporarily, and we generally have very tight control on RAM. And all of it means that OOMs are structurally impossible. And once again, it's much easier to run a cluster like this compared to what our customer may have to do. Our streaming engine is time aware itself. Flink and Spark are both way too general purpose, but there's a lot of structure in the problem of feature engineering. There's always a notion of time, and in fact, you do need that notion of time to be able to do watermarking, handling out of order events, time window aggregations, and so on. So our engine is itself time aware, and that is how we are able to do point in time feature creation, but it now also allows us to do point in time correct streaming joins, which are really powerful because, let's say you have a stream of Kafka events and you want to enrich those events with some information that lives in Postgres. That's effectively a join between Kafka and Postgres. And doing that in a time correct manner is very, very hard. But making our streaming engine time aware, this becomes immediately easy for us. There's no central scheduler. Everything is horizontally scalable for us. There is a supervisor there on each node. Each node picks up, divides work, and then they just go on their own. And this is another choice, which means that there is no synchronous communication and no single point of failure. These are some of the tidbits of the engineering that went behind in unlocking the experience choices I was talking about. You can always read more on our documentation and reach out to me or email as well. That's all I have. Happy to take any questions.
That's brilliant, Nikhil. Thanks very much. It's really interesting to see, the level of detail you've gone into.